Hello, Tokonami sir, are you there?
Yes, I'm here. Can you hear me?
Yes, sir, I can hear you, sir.
Okay. Can I resume?
Can we start, sir?
Okay, I'll do it. Okay. So I would like to introduce radon and trone reference chambers at our institute, Hirosaki University, Japan. Here is the outline of our radon exposure system. The system consists of 4 parts. Radon generation unit, mixing chamber, is an inner volume with 150 liters made of stainless steel, and monitoring unit. In this unit, radon concentration, temperature, and relative humidity are measured. Here is the exposure chamber. The value inner volume is 540 liters. This is our environmental monitor. Here is alpha gun to measure the radon concentration. Radon concentration is continuously measured by calibrated alpha gun. As I told you, environmental parameters are continuously measured by an environmental monitor. Regarding exposure chamber, this figure shows time variation of radon concentration at different exposure levels. Here I show you 5 levels. The lowest is about 300 becquerel per cubic meter. The low level 1,500 becquerel per cubic meter. Medium level 4,000 becquerel per cubic meter. 5,000 becquerel per cubic meter. The highest more than 10,000 becquerel per cubic meter of radon. As you can see, we keep the constant radon concentration in the exposure chamber. Here is a photo exposure chamber. Acrylic chambers of 540 liters is used for radon exposure. We confirmed the homogeneity of radon concentration in the exposure chamber. This figure shows an example of continuous measurement in a radon exposure chamber. Continuous measurement is possible under different radon concentration levels. The first case, radon concentration of around 800 becquerel per cubic meter. Then we change the radon concentration up to about 3,000 becquerel per cubic meter, like this. Also, we can measure the radon progeny concentrations, such as equilibrium equivalent radon concentrations. And also we took air samples intermittently to check the reliability of the data. Here, this is a square dot EERC from graph sampling method. This is polonium-218 concentrations. There's a good agreement between continuous monitor and graph sampling method. Here's an example of alpha energy spectrum and particle size distribution in the exposure chamber. During 0 to 1300 minutes radon concentration, about 800 becquerel per cubic meter, we obtained the alpha spectra like this. Polonium-218 and polonium-214. Regarding particle size distribution, count median diameter, it was 69 nanometer, and the geometric standard deviation was 1.9. After changing the radon levels, radon concentration went up to 3000 becquerel per cubic meter. Here's the alpha energy spectrum of radon progeny, the same as above. Regarding particle size is almost the same. Then I'll show you the outline of Toron exposure system. The system mainly consists of 4 parts. Toron generation unit, monitoring unit as the same as radon. Exposure chamber. In the previous, in the radon exercise, we use this chamber as a mixing chamber. But for Toron calibration, we need a smaller volume to get the homogeneity of Toron concentration in the chamber. Toron concentration is measured by Radon 7. This device is based on electrostatic correction method. We are using lantern mantles as a Toron source because this mantle contains relatively high thorium-232. Toron concentration obtained from Radon 7 is corrected by the conversion factor value with scintillation cell technique. In details for Toron generation system, open air go in through this filter and by pump. Then air was dried, this diffusion dryer, and goes through the flow meter and divided into 2 routes. The first one, this air goes through the humidifier. The other one is only just dry air, go this way. Then mixed air penetrate through this Toron source and go to the chamber, exposure chamber. Toron concentration depends on the humidity in the toron source container. The humidity is controlled using different flow rates of X liters per minute and Y liters per minute directions. Total flow rate is set at 10 liters per minute. This figure exemplifies the time variation of toron concentration. By changing the flow rate, we can set at different toron exposure level, like this. Relative humidity 10% is the green dot 40%. The maximum highest concentration is provided with high humidity, 60%. Therefore, toron concentration can be controlled between 3,500 and 30,000 becquerel per cubic meter. Here is the outline of radon and toron progeny chamber, aerosol chamber. The system consists of 5 parts: radon toron generator, aerosol generation unit, mixing chamber, monitoring unit, the same, and exposure chamber. In our aerosol generation unit, we use the aerosol generator model 3076 TSI company in the United States. Here is the relationship between flow rate of the aerosol generator and average number concentration. As the flow rate increases, the aerosol number concentration will increase. Also, here is aerosol particles are generated using sodium chloride solution, model 3079 with 1000 ppm, model 3076, the 500 ppm of sodium chloride solution. Aerosol concentration can be controlled between 800 and 230,000 particles per cubic centimeter by changing the flow rate of aerosol generator. Same. This device is a scanning mobility particle sizer, which measures a particle size distribution. The TSI company as well. This figure exemplifies the particle size distribution of aerosol, sodium chloride aerosols. With 1000 ppm, the median diameter was estimated to be 60 nanometers. But in the case of 50,000 ppm sodium chloride solution, the median diameter was estimated to be 113 nanometer. Aerosol size can be controlled between 60 and 110 nanometers by changing the sodium chloride concentration of solution. As you see here. Here's this concentration of sodium chloride solution in ppm. And this is a median, aerosol median diameter. This figure shows a time variation of particle size distribution with sodium chloride solutions. That's 10 ppm with 4 liters per minute. The particle size becomes stable at about 55 nanometers. In the case of 1000 ppm, particle size became stable at 70 nanometers. And in the case of 10,000 ppm, this is not so stable compared to a lower concentration. We also checked a different solution with potassium chloride. So you can see 100 ppm, stable at about 55. 1000 ppm, stable at about 80 ppm, 80 nanometers. If we took a higher concentration, the performance was not stable. Regarding exposure chamber, aerosol number concentration can be stabilized in exposure chamber. Here, the number concentration, you can see the concentration is stable, constant. Equilibrium equivalent radon concentration can be stabilized. Where are the intercomparisons organized? Here are examples of laboratories providing intercomparison measurements. I will show you 5 reference laboratories. The target of instrument in the UK, passive only, with radon atmosphere can be available. Every year, PHE organized intercomparison exercise. BFS Germany is also just for passive instrument. Radon atmosphere available. They organized intercomparison every year. Korea, this is India, Mangalore University, instruments, target instruments of active and passive. Radon atmosphere available upon request. Thorough check active, passive, and atmosphere radon and pollen upon request. our institute, we can offer the active and passive instrument test with both radon and thorium atmospheres. Upon the request, we can make intercomparison upon request. Here's an example intercomparison exercise. Yeah. From the applied radiation isotopes, international intercomparison. Our paper was published in 2009. International intercomparison of integrating passive detectors in the news radon chamber. So I show you the international intercomparison experiment of passive radon thorium detectors in NIRS chambers in 2010. The case of radon chamber, the number of participants increased year by year. And also we have some experiences on intercomparison exercise for thorium detectors. This table shows the participant list of type of detectors. Many countries participated in our intercomparison. Poland, Czech, Romania, Sweden, Thailand, Hungary, Ireland, Korea, China, Italy, Ukraine. So we set at least 3 different exposure levels. Low exposure, that means average radon concentration is about 1,000 becquerel per cubic meter. The medium this is not, yeah. We set different exposure level we control the time. The radon level is 1,000 or 10,000 becquerel per cubic meter. The time variation of radon concentrations is in our radon chamber. The radon concentration in the chamber is monitored by AlphaGuard calculated at PTB, Germany. In this exposure test, we also monitored temperature and humidity. Yeah. In this case, the average temperature is 21 degrees and relative humidity is 57%. These environmental conditions need to be realistic in an actual environment. In our exercise, 70 of results were in a good agreement with a reference value of radon concentration in the chamber. Yeah, this is a reference value. This figure shows the detector results with measurement uncertainty of radon exposure for all detectors during all experiments with percentage deviation of 20% from the reference value of the concentration. Reference value was given by our AlphaGuard calculated at PTB. 70% of result in a good agreement. In the comparison exercise in field, detectors of passive or active are usually used in field, not under standard laboratory conditions. Intercomparison under field conditions are occasionally organized. The problem is the true value. The quality control, we need to duplicate measurements, 2 or more radon detectors at the same place, and the relative percent difference among the set is monitored. Field blanks, a set of detectors accompanying the exposed detectors to check whether the expected background level is in expected limit. How are alpha track detectors calibrated? I will show the example with a passive radon tolerant discriminative detector. Let me explain the characteristics of radiator again. Radiator collaboratively developed by our research group and Hungarian company. The shape is cylindrical. The inner volume is 30 cubic centimeter. We are quite small. The detecting material is CR39. 2 detectors used with different air exchange rate because of therefore total contamination can be eliminated. Etching condition and track reading system is the same as previous system. Body material is electroconductive plastic, and here is an electroconductive sponge as a filter instead of the filter. This device is quite small, so it is easy to transport by postal service and easy to place. This is the overview of our radon reference chamber. Exposure chamber. Yeah. Here is a sampling port to take air samples from the outside. You can see here is alpha guard in the chamber to monitor the radon concentration in the exposure chamber. We placed radiate like this way. And here is the fan to make a homogeneity of radon activity concentrations in the chamber. Also, from outside, we measure the radon concentration with a radon 7. Regarding integrating radon concentration versus alpha track density, time variation of radon concentration, temperature, and relative humidity in the radon chamber during an exposure test. This is the radon concentration, temperature, and relative humidity. Radon concentration was measured by alpha guard, pulse type ionization chamber, which was calibrated by PTB, Germany. After taking radiate out of the exposure chamber, we proceed the data analysis And we got the result like this. The low air exchanger type, here is the time integrated radon concentration, the torque density. As you can see, the conversion factor for radon is the same. Yeah. This is a conversion factor. Same slope, 0.30321, 0.22 is the high air exchange rate type. Regarding iron tolerant chamber, as I mentioned in the previous slide, there's a humidity. Here's a humidifier, humidity control system. Here's the air. This is a tolerant gas generation unit and the grab sampling for calibration system. In our case, we use a Shinji cells for intermittent measurement. For continuous monitoring, we use a Radon 7 for radon tolerant measurements, tolerant concentrations, and also we measure the temperature and relative humidity in the chamber using the environmental monitor. This figure exemplifies the time variation of tolerant concentration, temperature, and relative humidity in the tolerant chamber during an exposure test. See, the tolerant concentration is here by the violet purple color dot is given as a tolerant concentration by Radon 7. And red one, tolerant concentration was given by scintillation cell. There's in a good agreement, as you can see. Blue line represents the relative humidity and temperature is here, almost stable. Regarding lower exchange rate type, it has low sensitivity against the tolerant. That's why it's a quite small calibration factor, almost nothing. On the other hand, in the case of high air exchange rate radiate, we can obtain the calibration factor very clearly. There are conversion factors for radon and tolerant concentrations by radiate in our institute from 2019 to last year, 2024. Here's a CR39 ID QRSH or something like this. Conversion factor is here, the low air exchange rate, high air exchange rate for radon, low, high for tolerant concentration. See. Conversion factors for radon and tolerant were estimated using radon and tolerant chambers, our institute. But calibration, as you can see, the conversion factor is not the same. Every time we have to check the quality of detecting material like this. Using the radioactivity detector, we conducted several radon tolerance survey in several countries. Japan, here. Mean radon concentration 22 becquerel per cubic meter, tolerance 22 becquerel per cubic meter. The ratio between tolerance and radon is 1.3. In Korea, South Korea, the radon concentration 62 becquerel per cubic meter, tolerance concentration 59. The ratio between tolerance and radon is 1.4. In Gansu, China, this area is famous for radon epidemiological study area. Radon concentration is 91 becquerel per cubic meter. But on the other hand, tolerance concentration is much higher than radon concentration, 365 becquerel per cubic meter. If we take the ratio between tolerance and radon, it was estimated to be 5.4. Yanjiang, China, as a H high background radiation area, 37 becquerel per cubic meter for radon, 728 becquerel per cubic meter for tolerance. The tolerance to radon ratio is 35.3. In Canada, radon concentration 110 becquerel per cubic meter, tolerance concentration 76 becquerel per cubic meter. Radon tolerance ratio is 0.97. Hungary, radon concentration 208 becquerel per cubic meter. The tolerance concentration 128 becquerel per cubic meter. The mean ratio between radon tolerance and radon is 2.4. Tolerance interference on radon measurements, I will introduce this topic based on our experimental studies. As you may know, there are many types of passive radon detectors used in major epidemiological surveys. Here's the EPAM, this is the electrolyte. The German detector, Karlsruhe detector, which was used in the first survey in Japan. This is a European, this is a very popular radon detector in Europe. This radon truck was used in the radon epidemiological study in China. Also, in France, they have two types of detectors, open detector and closed detector. This detector is similar to this. And also, Italy, they use the detectors sealed with polyethylene bag for tone entry control. Therefore, they can perfectly remove the toron contamination from radon signals. This table shows the relative sensitivities of passive radon detectors. Here's the measuring device, radiate low diffusion, that means low air exchange rate. This is a high air exchange rate type. Sensitivity for radon and toron. This is a prototype of radiate, namely Radopod. We modified the ordinary Hungarian monitor to measure the toron concentration. And so we obtained higher sensitivity for toron. German detector, which was used in the first survey in Japan, it has a higher sensitivity for toron. Radotrack, which was used in the radon epidemiological study in China, it has also higher sensitivity for toron, 68%. Regarding European detectors, popular detector, the toron sensitivity is quite low. Also, electrolyte EPAM has a lower sensitivity for toron. In Italian detector, as you see in the previous slide, by perfect sealing, they don't have any sensitivity for toron. Canadian detector used in the radon epidemiological study, it has also much low sensitivity for radon, about toron. And also I've explained the toron interference on radon measurement based on field experiences in epidemiological study area. We can explain the overestimate of radon concentration is like this. Observed radon concentration equals actual radon concentration plus relative sensitivity for toron times toron concentration. For example, when actual radon concentration and detected toron concentration are 100 becquerel per cubic meter respectively, radon concentration observed by Radotrack is estimated to 168. Look at this. 0.68% sensitivity for toron compared to radon. Therefore, the detector reading give the 168 becquerel per cubic meter. One more thing I'd like to tell you, even when European detectors are used, their reading might be overestimated if they are placed near the wall as an indoor toron source. This slide shows the measurement of radon without discrimination derived from first national survey in Japan. We used the passive radon monitor, German detector, in the first national survey. We checked the performance of this detector like this. Here is a geometric arrangement of the monitor. Here is a soil wall in a house. This is indoor. And we place a passive radon monitor at a different distance from the soil wall, from 10, 20, 40, 80, and 140 centimeters distance from the soil wall. And then we obtained the detector response of the monitor. See? Here is a distance from the soil wall and radon concentration evaluated. The radon concentration close to the wall is higher than that of the center of the room. This is the reason why the radon concentration is higher. Radon concentration in the first survey is higher than that than expected. We found a total interference on radon measurements. We have to pay attention, special attention to radon measurement, especially if the area has a high total potentials exist. We checked the performance of radiate. We checked the spatial distribution of radon and total concentration in a house with gypsum wall and a static condition, not the actual house, but the model room. This gypsum contains a relatively high activity, radium-226, 163, thorium-232, 522 becquerel per kilogram. We placed the radiate at different distance from the wall, gypsum wall. Here's the radiate. And the result. As you can see, the radon concentration, red one, is stable regardless of the distance of the gypsum wall. On the other hand, total concentration varies in space. Actually, it's the distance from the gypsum wall. Here's the source of indoor radon and toron. Radon is a ground soil from a few meter depths, partially building materials. In the case of radium-rich material, radium-rich rocks are used in the building materials. The toron source, building materials, from a few centimeters thickness. Therefore, even a small quantity of toron source, a significantly high concentration might be given. I'd like to show you our survey in China. We visited cave dwellings in China. Many people at the time, this is around 2000, between 2000 and 2005, we visited cave dwellings and we measured radon and toron concentrations in the cave dwellings. This is the schematic. And we placed the monitors in the center of the room. Here is a bed. People are sleeping there. And they cook inside of this room. Here is a dimension. The length 8 to 10 meters. The height is 3 meters around. The width 3 meters. Here's it's a one-way house. So we visited this area, Gansu province. As I told you, in this area, radon epidemiological study was conducted. Here's the intercomparison of our survey result with the previous study. The radon concentration for previous study, they gave them more than 200 becquerel per cubic meter with a radon track. These are US detectors. As I pointed out, this device was affected by Toron interference in radon measurements. Therefore, they didn't measure Toron and Toron progeny concentration. In our study revealed, the radon concentration is lower than previous study. 73 becquerel per cubic meter for radon, but Toron concentration is was high. Regarding Toron progeny concentration, 2.4 becquerel per cubic meter. But odd ratio is here. Due to the small sample size of our study, I can't say something strongly, but we need more study. We need more epidemiological studies here, if possible. Here are new implications and conclusions based on our study. Toron interference on radon measurements may result in incorrect risk estimate in several epidemiological studies on residential radon. Former studies might give us low risk estimate. So, according to WHO estimate, 20% risk is really correct? This is our question. Future studies or ongoing studies may give us high risk estimates. Therefore, radon concentration have to be accurately measured in any case. Quality assurance and quality control are one of the most important issues in the national radon strategy. So this is all my talk in this topic. Thank you.
Thank you very much, sir. Dear participants, if you have any question, you may please ask by unmuting yourself. Dear participants, if you have any question, please unmute yourself and you may ask the question.
Hello.
Yes.
Yes, Shinji, you may ask.
Hello. Hi, sir.
I can hear you.
Shinji,
Yeah, I have one. I have one small query that I just want to know that their radon has a specific contribution around 50, more than 50%, right?
Yes.
Among all
In the
the
worldwide average. Yeah.
yeah. So, what can be the contribution of the theron throughout the world average?
In my, if my memory is correct, maybe less than 10% compared to radon.
Okay.
Yeah.
Okay, sir. So, and the next is usually we study about the radon. So, why thoron study is that much important, or why people why people neglected this one earlier?
For example,
I mean, what are the benefit and pros and cons of this thoron study?
Okay, thank you for your question. Actually, in Europe or North America countries, radon concentration is much higher than Asian countries. But in Asia, as you see, there are relatively high thoron concentration were observed. Also, in order to analyze the risk due to radon isotopes, we have to measure both radon and thorium. Particularly, not thorium progeny need to be measured. Is my answer satisfactory?
Okay, okay, yes, sir. Thank you.
Any more questions, please? So if there are no questions from the participants, thank you very much sir, for this detailed and comprehensive talk. So we will resume this session again, the second session at 1:30 p.m. IST and 5 p.m. GST.
All right.
So participants will meet at the same Google Meet link at 1:30 p.m. IST. Thank you very much.
Thank you.